Hi everyone, welcome to another Wolfram language design review. This is part of our language completeness and consistency series, and we have a number of topics. First up, this is a horrifying one, around and min and numerical order.
Right.
Okay.
So we think we've untangled this, at least the symmetric case, and right. The question was, when how do we sort these, et cetera, and sort of one of the issues is, since these are all probabilistic, when do we say that they're actually different?
Yep.
And so,
okay, so the question is A1, A1 equals A2, obviously for this particular symbolic thing, it's just going to sit there. But
actually, right. it will not. So the key new idea is evaluate those two and compute A1 minus A2. So the key new idea is that we will consider two rounds equal if their difference is not significant, meaning their mu1 minus mu2 is smaller than the uncertainty. So that, that's it. Yep. Or proportion, right? So now we can continue. Okay. So we have to worry about these four functions: numerical order, equal, same key and order, and min. And these are the proposals.
Right. And basically order and same queue we don't worry about because they're not.
I'm not sure. I'm not sure I agree with you on that, but we'll get to that in a minute.
Okay.
Oh, wait a minute. Assign plus minus one. What does that mean? Oh, numerical order. I got it. I'm sorry. I wasn't reading properly. Okay. If the abs of the difference, why the heck are we doing this? Is less than twice the standard deviation?
So yeah, I mean, I think the idea is some multiple of the uncertainty is going to be like a tolerance with which you compare the centers of these around objects. And so it's like the tolerances that we use for floating point arithmetic. Equal, we allow 7 bits of difference. Same Q, we allow 1 bit of difference. So I think Jose could correct me if I'm wrong.
That's correct.
It's doing some multiple of the uncertainty and taking specific factors, one for equal and one, well, you're not using a different one for same Q, but that's a different story. Same Q for you is purely structural, I guess, on these objects.
Right. Yeah. So we are imitating what numbers do here, in the sense of having equal being more tolerant than numerical order.
Right.
And the question is 2 a good factor? So I mean, obviously it's going to need some kind of.
Well, this is like 2 sigma. Is that right? Is that how I should think about it?
Exactly. Yep. There are some plots below.
In the statistical discussion section. Right. So the key point is what we just basically said, right? The difference is significantly different from 0, and Jose and I are suggesting we do 1 sigma for numerical order and 2 sigma for less or for equal, I guess.
So 2 sigma, that's 5%. Is that right? What's the confidence? Is that 95% confidence?
Yes. And 1 would be 68.
Yeah.
So these curves were what we were suggesting the previous time, in which there was no notion of equality. It was always either +1 or -1. And now we have this intermediate region, the green region, which is equality. And so you see how now greater and less do never overlap.
Which is good.
Exactly. Yep. And so this is just
a little bit scary. I mean, this thing about having you know, it's a bit arbitrary, but of course it's been arbitrary for years what we do with finite precision numbers, and it has to be.
Yeah, it's a judgment call where we put the boundaries. But now the new thing is that there is a region of equality, and these are the 1 sigma, 2 sigma, 3 sigma, the red lines.
Is there any way of for our usual tolerance? There's no way of adjusting that, is there? And nobody's cared in 30 years.
Some people have cared, and there are internal variables that they can, you know, fiddle with, right? There's internal dollar equal tolerance, I think, and same Q tolerance.
Mark, you're the most likely person to have run across these kinds of things.
I wrote them.
Okay, fine. Okay.
And you know, we
because there are situations when you need to adjust the tolerances, like in hashing of numbers, you need to have a zero tolerance. Otherwise, you get like a floating point drift of things when you're doing like counting bins and stuff like that. And then if you do one method using a hashing and one method without hashing, and it all gets it gets to be a horrible mess. It gets to be method independent, the quadratic method and the hashing method and everything. So in any given method, you need to fix the tolerance of things that you're working on, and then you need to set that kind of as your universe, and then you need to kind of work in that. And so,
all right, so how's that going to affect this stuff here?
Well, it's a similar idea to what Jose's and Itai, I guess, are proposing here. I mean, it's we could argue about whether the factor of 2 there, or 1 or 3 or whatever is too large or too small, what it should be. It doesn't have to be a whole number. It could be like we use 1 bit, which is 0.3 decimal digits, the same Q tolerance of floating point numbers. So, I mean, but the concept is very similar to what we do for floating point numbers. So I think it's the kind of the right concept.
Okay, fine.
We just need to kind of decide which functions, what the tolerances should be, and that sort of thing.
Okay, so but we have this notion of oh my God, what are these called? System. Oh my gosh, what are the system settings? Low-level system settings.
They're internal. I mean, they're internal things.
No, I know, but what's our
reason.
usual wrapper for internal system settings? What's it called?
Are you talking
System
about
options?
System options. Yeah.
Yeah, I don't want to make it as public as system options, because these really are things that you should put in a block so they get reset within a specific small computation. System options are more things that you set globally, like the number of threads or something like that, and you just work with them in your session. But these are very local private things that you want to do on a very specific function.
And you don't think these are end user? You don't think typically this needs to be end user? I mean, the difference is
it's scary. The code is not prepared for everywhere, so that's why they're in internal context.
But let me make a point about this. With numbers, we have control. You know, if you have what happens if you have high precision numbers? What happens to these?
There you have essentially a very small interval, so very small uncertainty. So the uncertainty is around the last digit there.
Okay, so it's still a 1-bit uncertainty. Is that right?
We do have an example of that in the notebook, right?
No, but I'm sorry. I'm just trying to clarify.
It's what we're seeing right there, right?
Yeah, but Stephen's using very high precision, which would be a tiny interval. Your intervals are almost the size of the number there in your examples in the notebook. So
okay, but hold on. I'm just trying to understand. We don't do anything different with high precision numbers than we do with low precision numbers in terms of the last bit is ignored for comparisons or whatever else we're doing. Is that correct?
That's correct. Yeah. Order, for example, takes into account the precision, so it will look at the more precise one. It has a note. So order isn't purely structure, and that's one of the questions I have for Itai and Jose. So order for floating point numbers actually has some knowledge about the numbers. It's like doing an infinite precision kind of comparison, where it's like considering all the bits, and then it's kind of comparing the scales of them, the precisions of them, and stuff like that to determine which one comes before the other. So it's not doing a subtraction, but it is doing analysis of the floating point number.
Right, but it's based on the center, isn't it, Mark, of the interval?
Yeah, it's based on the center of the interval, exactly. Yeah, but
that avoids having a sort where you have a bunch of things, and you wind up with the first one much bigger than the last because of drift. And with your precision, with your definition, I could put together an example of a list that would sort in the wrong order because of your tolerance and numerical order.
Yeah, that is kind of a problem, and that's another thing with Itai and Jose's proposal. Their numerical order proposal is having a non-zero tolerance for the. I think you're proposing one. Yeah, which kind of is a little bit scary to me.
Wait a minute. Your point is, okay, hold on. Let me just understand this. So right now, with numbers, we have a comparison criterion that is based on a fixed number of bits in a number of any length.
Yep.
Those are allowed to be fuzz. Is that correct?
But not quite.
But not.
We have a comparison function that takes how many bits to allow when you compare the two things. And that can be 0 bits. That means it absolutely needs to take the entire number. And that's what order uses. Mm-hmm. Or it can be numerical order that says go all the way up to where the interval of uncertainty starts. That's like a kind of zero tolerance. Order would be like -infinity or something like that. And then we have equal that has like 7 bits. It allows like 7 bits of the number to be different. So like a precision of 2, when you subtract them, it will allow numbers that are close to each other to.
Okay, but so it's 7 bits still here, even though this is many more bits.
When you do equals, that's correct. But it's 7 bits in the difference of the two numbers that you're subtracting.
All right, so if I do this to the power 60, so this is plus 10 to the -60 times 7 bits is, I don't know what, let's say 32.
Log 2 of
base 2 of 10 times 60 or something like that. It's
percent 409 equals 410.
Yeah,
I see. Okay.
Yeah, and if you make that like a little bit more there, I mean, you might be just on the boundary with 32. So you make it like 128 or something, then it should be different. Yeah.
Right, and I guess finite precision numbers suffer from equality being not necessarily transitive.
Yes,
that's right.
Which,
and that's a problem with sorting.
Which our proposal also suffers from, but I don't see a way around it.
Yeah.
Yeah, but I mean, explain why you want numerical order to be fuzzy for these versus the way it is for numbers.
Well, I guess
because numbers, it's a zero tolerance. That's what Rob.
It's not saying. True. Look at the example on the left where it says 10.1 and 10.11, and those are still considered equal in numerical order.
Because when that 0.1 is an insignificant bit, so when you subtract them, you've got a tiny precision there, Jose. That's the thing. Your interval is so wide in that number that it's effectively only 1 digit.
But the number still remembers the 10.1. So the input form of that number still remembers. So I think there is some tolerance.
If you take x minus y there of that 10 backtick 1 and y 10.1 backtick 1, if you do x minus y, you'll get an input form of that. You'll get a 0. Yeah, if you look at the input form of that.
Yes, but the input form of y is still remembering the 0.1, if I remember correctly.
Yeah, but
so in a sense, something is ignoring that 0.1.
God, this is weird. I mean, welcome to floating point arithmetic, but yeah.
If we want to have numerical order with no tolerance with rounds, that's also fine with me. I mean, the thing is to have this some sort of choice of the levels of tolerance that we want for these functions.
Right, and right, and I mean, personally, I think it's quite weird if just, well, I guess part of the question is what do we do about min? And right, and I think,
but min will just be based off the choice that you use the numerical order. That's all it will do. It will just take whatever the result of numerical order is, if it's 1, -1, or 0, and it will do that, or either swap them or give you the first one or whatever. So min is just a consequence of numerical order, right. I think.
Yeah. But so let me just understand. The point of contention. So we are agreeing that equal is okay. We don't know if this 2 is the right number, but it might be.
Yeah, maybe.
Okay. All right. So we're agreed on that. So the question that remains is numerical order.
Mm-hmm.
And the argument that's being made is the numerical order criterion here, which is, wait a minute, is this the right way around, or should that be a half for 95% confidence? If the difference of the means, surely that should be a half there.
No, that one's no. 2. Because if you have two things that differ by a little bit, right, they're equal.
I'm sorry, I'm confused. This thing is less than, this thing is saying this quantity X.
Mm-hmm. Right, we're saying that then it's the, right, then if this is right, if that quantity is greater than 2 sigma, then there's a 95% probability that that difference is not equal to 0.
Oh, I see. I see. Okay. Yeah, I get it. So it's like when that thing on the left is getting really big, that's when it.
Right. That's when we can just say, oh, we base it based on the centers, because the probability that they're actually swapped, because these are Gaussian distributions, is negligible.
Yep. Okay. Okay. So the thing at issue is the numerical order case. Okay, so what are the arguments so what is Mark, what are you arguing for in that case?
I mean, we in the arbitrary precision code use 0 as the tolerance. So when you subtract the numbers, you must get a floating point 0.
Yeah, but I'm actually looking at it, Mark. Numerical order is different than order for this.
Yeah, your order is going to use even all the insignificant bits. It's like minus infinite precision. So numerical order is numerical order does this. It exposes a few hidden bits, does the subtraction, and then fiddles around and checks if the precision of that thing is going to be 0 or not, and checks if it's going to be like a 0
precision 0 test is analogous to the comparison with the standard deviation, is it not?
Yes.
Yeah.
But it's with 0 tolerance, right?
Well, yeah, but of course you have, right, because you have hard borders, right?
Yeah.
So isn't this directly analogous? I mean, if I say precision p, I'm losing p bits of precision. That means I have 2 to the minus p. If I'm, I'm not correctly seeing the math of this, but I mean, basically, you're saying it's a box whose size is determined by the precision. If the bits falling off the end of the precision thing, if it's precision p, any bit that is, it's 2 to the minus p, isn't it? That the box is of width 2 to the minus p, give or take.
If we're using p bits.
If the number is accurately a precision p, then anything smaller than that precision, any bits beyond the pth bit are undetermined. Therefore, the size of the box of indeterminacy is 2 to the minus p.
Right. Well, I'm just pointing out that when normally when we say P, precision P, we mean P decimal digits. So that's why I'm being.
Oh, I see. Okay,
when you're saying P, if the precision is P bits, then.
Yeah,
but I mean, internally it's all bits. So Stephen is just thinking like closer to the computer, which is how it's actually implemented, rather than
but anyway,
top level.
It's hard borders 2 to the minus p. So what you're saying is numerical order. If it is not within those hard borders, if it is within the hard border, it thinks it's equal. If it's outside the hard border, then it does its, whatever ordering it's doing, right?
Yeah.
Okay, so the question is, what is the analog of the hard border in the case of a round? And the problem is, a round doesn't have a hard border because guess what? It looks like this, it's Gaussians, right? So what do we do? In the case of numerical order, we, these things will be step functions. And, I have to say, I think it's reasonable, if I'm not being confused somehow, I think it's reasonable to use a criterion like this in the case where, because there is no hard border. Now the question is, the argument.
How? What? Yeah, the question is, what is the constant in front of that square root? That's the question.
I know. Well, okay, fine. Okay, so
I'm fine with decreasing it and having a half or something like that to be more strict.
Which means that you have to be in a closer.
Right. In order to be.
Go ahead.
You're right. That the probability of overlap is even greater than. Right. So the centers are much, that much closer than the standard deviation. So, right, there's at that point, the probability that you quote unquote have the wrong.
Well, let's compute those probabilities. It's just an ERF of some kind, right?
Right.
So what is the actual function of
well,
this isn't the same as like the student t distribution or something, is it? Where you're doing that's different. That's
no, it's right. I mean, we have that computation in the statistical discussion section, right there, ERF C.
Okay.
Yes, and it's interesting to see that that quotient that we have been looking at appears there naturally.
The 2 times this 2 times
the difference divided by the square root of the sums. You see, it's the two. It's right. the elements of the subtraction of the 2 arounds, center and standard deviation.
I get it. But I mean, okay. So that's the abs. But now there's a square root of 2 here, which we could presumably take out of the ERF, could we not? I don't remember the relations for ERF. It's not like an exponential where we can trade it out. But that square root of 2. Okay, so if we take this, we're asking the question is you change that number. I'm pretty confused.
I think
you should look at the plots. Maybe looking at the plots will be helpful.
The plots at the bottom.
Right, and that one right there, I think, is the most helpful. Right, so the blue area is I
think I think the 3 at the bottom are clearer. The ones for 1 sigma, 2 sigma, and 3 sigma.
Oh, okay, yeah.
This one here?
No, further down. These 3. So, for example, if we have the 2 first Gaussians, do we consider that those are clearly separated? That's the meaning of 1 sigma. And for example, we might say there is a lot of overlapping, but if you think the center of the yellowish distribution is clearly at the tail of the blue.
Okay, you know what this reminds me of? It reminds me of like the Airy criterion in diffraction.
Yeah. So So why that's a function right there that you can So why don't we plot 1/2 sigma and see what that looks like?
1/2 sigma being what you are proposing if you had a 1/2 instead of a 1. This is what you're currently proposing for. Okay, can somebody? Whoops.
Did we need to
sigma?
define sigma?
Oh,
Sigma is defined, sorry. Didn't realize we had that extra input there.
Remind me what the area criterion is. It's that the first minimum, you know what I'm saying? You guys remember this in diffraction, right? The 1.22 lambda over d business.
Yep.
Right, so that the area criterion is that the first minimum of the diffraction peak that you are, I mean, maybe it's different because it's a question of what you visually perceive there. So it's a different type of thing. But this is the same kind of question, I think.
Right. I mean, it's given a a wavelength lambda, what's the smallest area you can resolve based on the diffraction pattern.
Right.
Or length scale you can resolve, not area. But
right. Right. But okay. So listen, let's understand what you're saying here. So you're saying the criterion is, in this case here, the 2 sigma case is the case where those two things are considered equal as soon as they are closer than this. Is that correct? That's the equal criterion.
Exactly. So those two Gansians will be, that's the border of separation between being separated or equal. And it's quite far already.
Huh. You really think it's okay to consider them equal when they're that far apart?
Yeah, that kind of worries me too.
So that's what I'm saying. 2 sigma may be already very tolerant.
Maybe too tolerant, even for equal.
Exactly. Yeah. Yes. I mean, equal sometimes feel a bit too tolerant, but but
okay. So one criterion is, you see that little dip there.
Mm-hmm.
For what? This is like, are you a bimodal distribution or is it all smooshed together?
Mm-hmm.
For what sigma? I mean, and clearly that's going to depend on the width of this thing here.
Yeah.
I kind of think that if this is all a smoosh distribution, it never goes down. Of course, we're not seeing the sum of the distributions here.
I don't think that's a very arbitrary criterion. I mean, there is we could try, I forget what the formula is, but there is the formula for, what's basically the p-value that the means are different, given the two, means and standard deviation.
That I think is the student t-distribution, is it not?
Well, right, when you have a small sample size, you use the t-distribution. But if you have a lot of samples, I think there's just a formula given the means and standard deviations of the normal distributions.
And we're effectively assuming infinite number of samples in this case. We're assuming we actually have the distribution.
Right, the sample number doesn't enter into it.
Right. So you're suggesting in the shocking you're suggesting a p-value criterion.
Yeah, maybe. I mean, I think it's better than something arbitrary like just how the plots line up with each other.
Right, and these plots are a little misleading, right? Because exactly how much they look like they overlap depends on the particular sigma 1 and sigma 2 chosen.
All right, well, so what p-value, assume that we can do this with p-values, which we can clearly do, right? What p-value, what probability of the means in fact being different would you want to take for the case of equal? Would you be satisfied? Would you consider them if the probability that the means are
right? And so my objection to 1 sigma is, all right, so you're going to say that this is less than this when there's in fact a 32% chance that these numbers are equal, right? That if you draw an infinite number of time, 32% of the time, the values will be, reversed essentially.
Okay, hold on. Okay. The question is, given these two distributions, what's the probability that the true mean let's see, well, you're asking for reversal, but I'm just saying the probability the true means are equal is not something you can compute, because that's a point thing from a continuous distribution, is it not?
You know, I don't know what you mean by the two means are equal, right? I mean, we know what the means are and they're not equal.
Given that we know the distributions exactly.
Right. The correct question is, given, okay, what the heck is the criterion?
Right. I mean, this is why we started out by computing the probability, you know, given, you know, our mu1, which we took to be 0, and our mu2 that we call to be mu, what's the probability that, you know, x1 is less than x2?
Okay.
Right. And then we, right, and then
what on our live stream suggests that we look at this thing here, receiver operating characteristic.
I have never heard of this thing. I'm not even sure what field we're talking about.
Binary classifier system discrimination threshold is varied. This does seem relevant.
I mean, we can study more probabilistic characteristics of this problem, but I think we just need some sort of judgment call to make this work.
Right.
And then if we have to adapt it in the future a bit to change the confidence levels, we can, but.
This seems relevant. Thank you for the suggestion here. I think this is relevant. Oh, look at this.
This type of approach would require a new function in which we can specify in a separate argument the level of confidence that we want, or p levels or whatever. But I think we want something automatic.
No, I agree. What is this whole thing?
We have a setting like we have for equal tolerance and same Q tolerance, which is hidden but could be set on a block. That would be the.
No, I understand, but that's an escape valve.
Well, sure, of course it is, but.
Okay, let's look at this receiver operating characteristic, which I have never heard of.
Mm-hmm. Yeah, we will.
All right, but we're going to pick two numbers, and they're somewhere between 1/2 and 2, probably, and that will be our default. And we can have an escape valve, and I think that's where we should go.
And around is still experimental, correct?
It is, yes.
Right, and so yes, and you know, which right. I just mean I was just saying, you know, we could maybe make the escape valves perhaps slightly less hidden, or just sort of tell people.
Let's make them hidden. I don't think they're ever going to be relevant. Let's just, you know.
Well, I'm just thinking if we get feedback, it's too strict, it's not strict enough, then, you know, it might be useful for people to be able to tweak, but.
I see this, the thing that's interesting here in this curves, this is, you know, false positive rate, false negative rate, true positive, true negative. So that's a way of characterizing, if you've got these two distributions, right, it's the criterion. This will be our false negative rate is our rate of thinking they're the wrong way around, so to speak, is our rate of having the variables assigned the wrong way around, etc. Does that make sense?
Mm-hmm. Right. I'm not sure we ever heard, or maybe I just missed it, you know, Mark's objection to same Q.
Yeah. No, same Q is fine. It's just structural. But I was wondering about order. So you talked about numerical order, that's numerical values. But how does order sort around objects?
Well, I think
if it doesn't take it
by centers, right? By centers, and then using the true order on the numbers. Because
so it
centers
sorts
are
by
the first
centers.
segment.
Yeah, so, but that is like numerical order, but that's like with an infinite or using all, ignoring the uncertainties. Right?
Exactly.
Yeah. Okay, then that's absolutely fine. That's exactly what I think it should do.
Yeah.
Okay. Right.
Exactly.
Yeah.
So
Yeah.
No, I just thought it didn't take a no. Yeah. So it is kind of related. It's like having the constant zero in your
order and SameQ are already doing the right thing here because of the structure, because having the center as first argument.
Yeah.
All right.
Yeah.
We can declare victory here.
Okay.
Let's
Do we
move
want to talk a bit at all about the antisymmetric case?
Oh, you mean the asymmetric case?
Yes.
Asymmetric case, yes.
Yes. Right. And which our proposal is basically to do the same thing, only, we first, compare the centers to decide which sigma faces the other and use those is the basic idea.
In the asymmetric case, the distribution is broken into two pieces. Is that correct?
Correct.
Yeah.
Yes, it is.
Well, yes,
the distribution of one asymmetric around is two half Gaussians, right?
Right. Which it's a discontinuous as a function of variable value. It's a discontinuous. P of x is discontinuous in x.
Right.
PDF of x is
right. I mean, one could have a discussion of, is that the right model? But that is the model we are currently using.
Yeah, that's the model we're using. I think any other model, I mean, you're chasing, the whole point of a round is you've got some rough estimate of how much error there is in something. And, by the time you're saying, well, actually, it's this particular, asymmetric distribution, well, then you're using completely different technology.
Mm-hmm.
Yep.
Okay, so you're saying, look at the facing sigmas, so to speak, and then apply this criterion.
Right.
Which means that, are there sort of paradoxical cases where you have a very, very wimpy, opposing sigma in which...
Yes, exactly, right. So you can have a case where, what the center that is higher has a probability of being, asymptotically approach 3/4 of being less than the lower center.
There are examples, if you open the
there are
statistical.
examples in the statistical discussion section if you want to take a look.
So this case, for example, we consider them equal because the overlapping is large. The long tails are facing precisely each other. So they overlap a lot. This criteria would say that these two are equal. While if you face them the other way, farther down, they are different. Because they overlap very little. And so that side is very precise in a sense.
Oh, boy. Well, in that receiver operating characteristic thing, for example, what matters that, it seems this is the whole question about what's the area of overlap.
Right.
Seems to be the thing worth thinking about, which is an integral, which means that number isn't a pure ratio of standard deviation to difference of means. It's some inverse Earth type thing about, I would have thought that the criterion should be something about the size of the overlap integral as compared to the size of the non-overlapping parts.
Which is essentially what we're simplifying by, so, right, in the symmetric case, that's basically what we're doing exactly, right? We're just, using a multiple of the standard deviation as opposed to, and here, yes, we're cheating a little, but it's not,
What is your proposal here for what to actually do?
Right, so we take the two centers and order them as if they were exact or, whatever precision numbers they are. And then we, use that to determine which of the plus or minus is facing the other center, and use that in the standard to compute an effective standard deviation, and then use the symmetric criterion. And in the top place where the large standard deviations are facing each other, right, we see a large area, there's a large area where they can be oppositely ordered, and we declare them to be equal because they're both sort of near the middle.
But I don't understand why the criterion isn't. If the overlap area divided by total area is greater than blah, then they're considered equal. If the overlap area is less than blah, let's say the overlap area is 95%.
Well, first of all, define overlap area.
But it's going to, in the end, it's going to be similar. It's just that we want a criterion which is fast enough to be computed.
Okay, so you have to approximate that. But I mean, if what we're thinking about is what's the probability that there is,
right? We're looking at the negation, right? Our equality function, right, is 1 minus the probability that one guy is less than the other, and minus the other way. And we're looking at when is that large.
So we can test your idea, and I think it's going to end up being something very similar. But
fine, I'm sure it is too. I'm sure you can approximate it very well by some purely arithmetic criterion, so to speak, that doesn't involve earths and so on.
Yep.
But I mean, assuming it was an integral criterion, what would we want the ratio in order for the things to be declared equal? What do we want the overlap probability to be?
I would say very similar numbers to the ones we use for the symmetric case.
Which is what, 90%, 95%?
Yes, if we are using like 1/2 and 1 sigma,
or 1/2 and
1 and
2 sigma.
2 sigma was what we were using before.
Yeah, 2 sigma.
Okay, so final question then. Numerical order as compared to equality test, same criterion or different criterion?
I would say numerical order has some sigma multiple which is smaller than 1. I would say 1/2, 3/4 of sigma.
Okay. All right, let's just see what this means for the overlap integrals, and then I think we're done. Okay, can we move on?
Yep.
Okay.
All right, Bra and Ket.
So this is, something we discussed possibly pre-pandemic. It took so long for somebody to go and do this, but it's, so now we're just talking about the documentation.
BP as opposed to AP before pandemic. No, we don't even have an AP. Anyway, who knows? Okay, so the only question here is whether it's bare args or whether it's a list.
And it wants to be a list, which is...
Why does it want to be a list?
Because when you put a Bra and a Ket together, that has to be 2 arg.
Wait a minute. Why does...
It's for consistency with Bra Ket.
I see. That does make sense, yeah. Do we have anybody here representing the quantum framework? Is the quantum framework going to use this directly?
I don't think we have anybody representing the quantum framework.
Okay, well, can somebody check with them? I mean, it looks okay to me, assuming they're happy with it.
Okay.
Yep, we can check with them.
Okay, let's go echo here.
Right. So, this is, a big, messy discussion. So I don't know that we...
Well, let's give it a try for a minute. Yeah. Okay. What we've talked about previously is, let's see, where did we get to last time? Didn't we already have a discussion? Okay.
Well, we had a 5-minute discussion at the end of.
Okay. All right. Okay. So let's describe what some of the things we think we want are. Goals. Okay. So you know, put a wrapper around a whole evaluation to sort of panelize / limit / whatever echoes within it. That's one type of thing. Another thing we want is for a single echo, make it not generate too much stuff or panelize itself. Is that a fair concept?
I thought we had shelved that idea.
Okay, well, tell me where we got to before.
Well, you know, there's the list of the functions that were discussed in the last time we had a serious discussion. And, you know, I'm not sure we're going to, you know, page in and move beyond that in the few minutes that are left. Well,
okay, so you're suggesting that we table this for a custom echo discussion, basically.
Sure.
What else do we need to prepare for that discussion? Do we think we have the use cases understood?
Well, I mean, there were, well, it's not clear to me that we have the use cases understood. And
that's what I was trying to write down, what some of the use cases are. I mean, the basic point is, you're trying to balance the number. I mean, it's essentially, okay, echo is being used as a diagnostic, but once you've seen it a few times, it's enough. You don't want to, I mean, the cases where I've literally had the thing running that's generated a, you know, 100 megabyte notebook, just echoing random stuff out when I didn't know it was ever going to trigger. Right? I was just like, is it going to trigger or not? You see what I'm asking? Where you don't really want it, you know. Okay, you're asking the question, does it trigger? Okay, you see five triggers, 5, you know, actions of it. That's presumably, you know, then that's enough. You don't want to see it 100,000 times. That's one use case. What's that?
Well, I mean, I would agree you don't want to see it 100,000 times, but I disagree that the lower limit is 5. I mean, when I'm actually debugging these things, it can easily be dozens.
Fine. Okay. Well, the question is, okay, what's the criterion? What is the criterion to shut it up? Okay. So A, you've seen it more than X times. B, you've seen more than X echoes altogether in this input line. What's another criterion?
Right, and you're imagining something where just all you have is echo and there's no outer wrapper?
No, I'm saying we could put an outer wrapper around the whole thing to determine this. The issue is, okay, so, you know, for example, we could have, you know, an echo, okay, echo control, right, of expa. And maybe we have something where we can say, we can put an echo control there that has a nice sub value. Where you say echo control and you say, 5 or something, and that means, I don't know whether that's per thing or whether that's, maybe this means that's the maximum per thing, and then this is the maximum total and things like this.
Right. Right. I mean, so you'll notice that I have a suggestion of using echo quiet the same way there, right in the middle of
Quiet
the
echo. Yeah.
But of course, you would we would need to implement, actually implement hold all subvalues before something like this could work.
I see.
Right. Otherwise, all the echoes would evaluate before the quiet echo.
Yeah. Okay. Fine. But we could do the case of this without subvalues, without solving that problem.
Sure. But
the subvalue case is more useful. But okay, the cases that again another goal is some evaluation produces lots of echoes. When it's finished, get rid of them. That's echo cleanup or cleanup echo.
Yep. Okay. So I don't think you're right. I don't think any of this is significantly different from what we discussed last time.
Yeah, I agree. So we need to home in on what we really want to do. But okay, Dan on a live stream is suggesting, what about redirecting echoes to a different window or file?
Yeah, so and one of the things I was going to ask, not being an echo expert, is so echo has the side effect of creating a thing in the front end, potentially. Does it have any other side effects?
No.
Because and the reason I ask is because managing a stream of echoes looks a lot like a log file.
Sure.
And one of the things that makes log files useful is being able to process them symbolically.
Well, that's an interesting point.
I mean, how do people process a log file that is hundreds of megabytes? They're doing things like filter by time, filter by the name of the event, filter by, some other criteria that is being symbolically collected, and then show me only the relevant stuff.
That's like echoes as so reap kinds of things.
Kind of, yeah.
So, I mean, that, you could imagine something that says reap echo.
And so, I mean, maybe sometimes, it's maybe you kind of want to see the 100 megabyte stuff because it's going to take some exploration to figure out what the relevant portion of it is. And when I say see it, I don't mean literally embed it in the notebook. I mean, but have it available to you for exploration.
Right. I mean, this is okay. Another case is redirect the echoes somewhere else.
Like print action.
Yes. Which we don't have for echo, right?
We do not.
Right. That was another suggestion that I thought we had tabled in favor of the list that we had at the top here.
Well, okay. You're telling me basically we can't solve the problem right now. But I really think this is the thing we should, we need to address. It's a very useful piece of functionality, but go ahead.
Yes, well, there are details we need to get into, and each time I bring this up, you get distracted by this grandiose vision and never discuss the details. So,
okay, example of detail.
Well, like this dollar echo limit. I don't know. Right. A, the name is wrong. B, I'm not sure what it is we're actually, what it is we want to apply here and how we get there from here. So
this is a more complicated discussion. You're right. We kind of run out of time here, so probably we should wrap this now and expect to do a custom meeting just about Echo.
Okay.
But
Or just have it first on the agenda for a change. It's just that the around stuff, what since we could foresee getting around stuff done for 13.3, that took precedence.
Fine. Okay, sounds good. Anything else for here right now?
Nope.
Okay. See you all soon. Thanks to folks on the live stream. Some good suggestions there. Much appreciated. See you all soon.